So this section's just to say a little more about inverse functions and some of the features. So let's look at f of x on the left-hand side of the screen. That's 2x plus 1. Let's say we were going to evaluate that function at 3. What are the things that we would do to that value, and in what order would we do them? So first we would multiply by 2, and then we would add 1, which would result in 7. Now, looking at the inverse function, which is over on the right-hand side, and that little -1 exponent, that's not really an exponent, that's just a notation or way of writing f of x that tells us that that is actually the inverse function of the function that's on the left-hand side. So let's think about how we would evaluate and in what order. So this time I want to think about plugging in 7. And if we're going to evaluate the inverse function at 7, what would we do and in what order would we do it in? So the first thing that we would do is subtract 1. Oops. 7 minus 1. And then after we did that, we would divide by 2. So we would do this, and we would get 3. So here's what I want you to notice about this. If you haven't noticed already, we're using opposite operations. And in addition to that, they are in the opposite order. So in the first function, we're multiplying first and then adding. And then in the second function, we're doing that subtract 1 and then divide by 2. So not only are the operations flipped, but the order of operations is also reversed. And it will be like that in inverse functions. Now sometimes the simplifying looks a little bit different, so it may not be obvious that it's the inverse function because of the way the numbers simplify. But generally they'll have these features. I would suggest you pause the video and follow the same procedure. So if we were plugging in a number for x, let's say we were plugging in 2. What is the order that we would do things? Well, first we would cube the 2, and then we would multiply by 2, and then we would add 1, and that would give us, let's see, 2 cubed is 8, times 2 is 16, plus 1 is 17. Now let's look at the inverse function. So to remember, that little -1, that's actually not an exponent, it's just a notation that says, hey, this is the inverse of that other function f. So let's think about plugging in a number, say maybe 17. If I want to find the inverse function on 17, what order would I do things in? So that inverse function is going to subtract 1 first, and then it's going to divide by 2, and then it's going to take the cube root. And so what I want you to notice also, besides the operations being opposite or inverse, that the order is also inverted. And the input, so the x value of our function gives us a y value. Notice that that domain value and the range value are switched around. So if I plug in my y value into my inverse function, I get out x. So this function does something to the number, and that inverse function does exactly everything you would need to do in order to just get x back. And that's why these functions are important, especially if you're talking about something like encoding and decoding, or direction somewhere, getting back. You do the opposite in the reverse order. So the inverse function is denoted by f with a little -1, and you are going to read that f inverse. In a relation, we have pairs of elements of the domain that match the elements of the range, okay? Well, in an inverse function, those orders are reversed. So if AB is in F, then BA is in the inverse of F. Okay, so it switches the X and Y, or it switches the domain and range around. I'll show you some examples here in a table so you can see what I mean. So that's why we say the domain of F is equal to the range of the inverse function, and vice versa. So here's just a couple of diagrams. Say I'm plugging in some X value into a function and I get some expression out. The inverse function does exactly the opposite things to get you X back. Same thing down here, they did it with apples and bananas. So these are just some visuals to kind of give you an idea of what does inverse function mean. Well, it's just the opposite. It undoes all the things that were done in the first function. Here's another example just showing you how if you plug in a number into the function and you get out an answer and then you plug in the answer into the inverse function, it gets you back what you originally plugged in. So you can pause the video and read through those. This is an example of a composite function. Basically what that means is you do the first original function first, and then whatever you get out for your output, you're going to plug that into the inverse function, and it returns back your original value. Or you could switch the order, so I could have some output from my inverse function, plug it in to my F function, so that's why these are kind of nested into each other. This is also called a composite function. That's where you plug one function in for the variable into another function. So you're always going to return back that value, no matter what it is. So I want you to look at this table and think about what do you notice. You may want to pause the video. But you should notice that list 1 and list 2 are basically opposites. So if list 1 were my f of x, then list 2 would be my inverse function because the domain and the ranges are switched. Domain switches with range. So notice that these are flip-flopped. -1 goes to 3, -3, now -3 goes to 1. 0 goes to 2, now 2 goes to 0. So it's just swapping those x and y's. Here's the same concept, but in graph form. So say I have some relation G, and it has these points that are listed here in this table, which are also graphed in blue. So here's my G of x, and those 4 blue dots are already represented on a graph. Take a second and fill out the inverse of those into the table. So you may want to pause the video because I'm going to fill them in myself, but I want you to try it. So all I did was reverse the x and y with each other, and now I'm going to plot these on the graph. I want you to pause the video, try plotting them on the graph also, and look at it and see if you notice anything. There's my plot of the inverse points. And what you should notice is there seems to be some kind of symmetry to it, and in fact there is. If we imagine a diagonal line, which I'm sketching in now, the line y equals x, then notice that my function points, if I had reflected those across that diagonal line as if it were a mirror, then we would actually generate our points for that inverse function, and that's always going to be that way. So even if I have some kind of continuous graph, then the inverse of that is going to look like a reflection. Here are some examples of functions and their inverses plotted on the same coordinate plane in that diagonal y equals x, where we're reflecting the function to the inverse function, and the reason why it looks like a reflection across the line y equals x is because the x and the y coordinates are switched in those plots. So that first one's a logarithmic graph, an exponential graph. Then over here we have, in the middle, we have a quadratic that gets reflected, and then that one on the right is a cubic that gets reflected.